Hello, my name is Miguel, and I'd like to teach you a few things about muscle fibers and contraction. So, let's go. Now, we characterize muscles anatomically to be connecting to bones via tendons. That allows the muscles to move the bones and cause the motions that we know of, like walking, moving our arms, writing, and all that sort of stuff. Now, the muscles themselves can actually be subdivided, can be broken down into smaller units. As you can see, if we have our muscle proper right here, this entire thing, the muscles themselves are comprised of fascicles, these big cylinders of connective tissue that themselves contain the myofibers, fascicles containing myofibers. The myofibers themselves are the smallest unit of the muscle. Basically, they represent the skeletal muscle cell, one skeletal muscle cell. Within each myofiber, there are two main organelles that allow for contraction. You have the myofibril. The myofibrils are the organelles that actually do the physical action of contracting and shortening. And then you have the sarcoplasmic reticulum. It's such a fun name to say. It makes you feel so smart if you say it correctly enough. It's like sarcoplasmic reticulum. Um, Basically, this organelle, the sarcoplasmic reticulum, is what stores all the calcium within these muscle fibers. Calcium being the sort of connection between the nervous system stimulating the muscle and then the actual muscle contracting because of the calcium. We'll get into how that happens later on, but there's still a little bit of microanatomy that we'll have to go through for the myofibril itself in order to understand how contraction works. So going forward, you've probably already heard or talked about or studied that the myofibril themselves has two main filaments. You have your thick filaments right here. Thick filaments being the ones that are made up of the protein myosin. So thick filaments made of myosin. And then you have your thin filaments that are made of actin. Actin you've even probably heard of as in creating parts of the cytoskeleton as well. So actin for thin filaments, myosin for thick filaments. Now, the thin and thick filaments, whenever you have muscle contraction, these thin and thick filaments will overlap with each other. This is what you call a resting myofibril right now. The filaments already kind of overlap. There's no contraction necessarily going on. But when contraction does happen, there is an even further overlap of these thin and thick filaments. As you can see, these thin and thick filaments will come ever closer together, and this will effectively allow the myofibril to shorten to such a dramatic length, allowing the entire muscle on a macro level to shorten as well. Now, we call these overlapping regions of thin and thick filaments specifically sarcomeres. Basically, the sarcomeres are these sort of regions of thin and thick filaments that, along the length of a myofibril, are end to end, So, for example, if I have this as one sarcomere and this as one sarcomere, these would just go along the length of the myofibril, each sarcomere containing these thin and thick filaments. Each sarcomere itself contains, or is bookended, I should say, by two Z-lines. The Z-lines being these structures that are actually attaching to only the thin filaments. And these structures are the ones that actually do the contraction, or that are most dramatically shortened or brought together because of the contraction. So the sarcomere will shorten as a response to contraction, as you can see, the Z-lines coming together. Additionally, there's also the M line, the M line just being a line that goes straight down the middle of the thick filaments. It's just along that axis of the midpoint of each thick filament, just going all the way down. The last three landmarks that I want to talk about are the landmarks based on the overlapping patterns of the thin and thick filaments. In the area or the region that the thin and thick filaments will overlap, you have your A band right here. Next, you have the region where the thin filaments only exist without any overlap with the thick filaments. So that would be your I band. And finally, you have the region where only thick filaments exist with no overlap with thin. That would be your H zone. It changes from band to zone for some reason. I'm not too sure why. But for the most part, you can kind of imagine that the H zone itself in a contracting sarcomere, in a active sarcomere, this H zone will actually disappear because the thin and thick filaments will fully and completely overlap with each other. So there's no region where it's only the thick filaments and no overlap with the thin, at least in a contracting sarcomere. In this resting one, as we see here, there is in fact an H zone, but just remember, when the sarcomere actually contracts, you have no H zone. That H zone disappears. One way that I remember all of these, because it might not necessarily be too intuitive, is I made a little bit of a haiku. I'm not really a poet, so it's not the best haiku, but I try my best. As you can see, the haiku is, I want to be thin. Now, everyone has their ideal body weights. At least for me, I want to be a little thinner. I want to lose a bit of weight, so I want to be thin. Next, you have someone who might want to gain a little bit of weight. He wants to be thicker, or he wants to be much thicker, right? So I want to be thin. He wants to be much thicker. And finally, the last verse, which is a fun overlap. So as you can see, each letter, each beginning letter of each verse correlates with one region within the myofibril. I for the I band, I want to be thin. H for the H zone, he wants to be much thicker. And finally, A fun overlap, A for the A band overlapping region. Cool. Now we can actually get to the sort of molecular basis of contraction. Now, before we look at all of the structures, I do want to just give a quick premise going back to the beginning. So whenever we start with contraction, remember that we have typically a neuron. As you can see right here, a neuron sending off a signal via neurotransmitters, namely acetylcholine. It will send off acetylcholine through this neuromuscular juncture, neuro for neuron, muscular for muscle, the junction being the sort of area between the synapsing neuron and the muscle. It sends acetylcholine through this neuromuscular junction. The acetylcholine will then attach to receptors on the muscular side of that junction, and when those receptors actually bind to the acetylcholine, that will cause an action potential to propagate through the muscle fiber. So, like neurons and their axons, there is an action potential that goes through the length of the myofiber. Now, when that action potential starts going through the myofiber, the sarcoplasmic reticulum actually detects that and releases calcium in response to it. This is done through voltage-gated calcium channels. So once that action potential is felt and detected by the sarcoplasmic reticulum, basically those voltage-gated channels will open up and allow calcium to flood the myofiber. The calcium is what actually allows the contraction to initiate, because whenever you have no calcium, whenever there is no action potential, the resting sarcomere will have this troponin-tropomyosin complex over the actin filament. Now, this complex here will basically cover all of these binding sites, as you can see right here. These binding sites are actually for the myosin, specifically, for the thick filament, specifically the myosin head that comes off of each thick filament. So, in a resting sarcomere, when you have no action potential, no force to actually cause contraction, you have this troponin-tropomyosin complex covering the thin filaments and preventing any sort of sliding action, any sort of interaction between the thin and thick filaments. So, when calcium comes, calcium will bind to this globular protein on the troponin-tropomyosin complex, the globular protein being troponin, namely. Once it binds to the troponin, this whole complex will actually shift off of the binding sites, freeing the thin filaments and allowing the thin filaments to be at least bound to the myosin heads of the thick filaments. So troponin, troponin-tropomyosin complex is on the thin filaments. Calcium comes, removes the complex off of the thin filaments, and allows the binding sites on the thin filaments to then be bound to the myosin heads. And just a note before we actually get that binding action, the myosin heads themselves are already bound to an ADP and an inorganic phosphate group. Now, those two groups are actually from the last contractile cycle, right? So, for the most part, these groups here, they are already pre-existing. We'll figure out, or we'll, get to why these groups are already there when we get to later stages of the contractile cycle. But for now, just know at the very beginning of contraction, when calcium first enters the cell and removes the troponin-tropomyosin complex, there will be an ADP and an inorganic phosphate bound to that myosin head. So, whenever those binding sites are then released, you will have the myosin head basically in this sort of high energy conformation where it is just dying to go and actually bind to these myosin binding sites on the thin filament. So, the myosin head will connect and bind to the actin filaments. This actually forces the inorganic phosphate of each myosin head to go off, and then the actual contraction happens because the myosin head will, from its high energy state right now, it's kind of like firing off a slingshot where so much tension is building up that once that tension is able to be released, it'll just bend forward and go into this lower energy conformation. This in turn actually releases the ADP it was previously bound to, but then allows the actin filament to further slide and create that contraction, that further overlap that we were seeing whenever we looked at the sarcomere, as you can see. So that further overlap is caused when the myosin head kind of turns from a high energy conformation to a lower energy conformation. The slingshot building up all that tension is finally released, and now the myosin head is in its lowest energy state. Finally, we have that contraction. In order to reset this, kind of like, you're pulling back that slingshot again, you're going to need to put some energy into the system. Now, the main sort of energy molecule that we all know of, ATP, is also going to be involved here. Basically, ATP, whenever contraction is going to be done, ATP will bind to each of these myosin heads. That allows for the myosin heads to, 1, release from the actin, from the thin filament, and in that process, the ATP gets instantly hydrolyzed. It gets instantly consumed so that we then form an ADP and an inorganic phosphate. So like I said, that ADP and that inorganic phosphate, those are coming from the last contraction. So, as you can see, they're kind of just remnants. They're kind of like a reminder that, hey, a contraction happened before this oncoming contraction that's coming right now. So, as you can see, everything is reset, and now you can finally redo the cycle, the contraction cycle, all over again.